Hi everybody. This video is going to explain to you and use an example to show you how to calculate the generalized linear F-test for regression models. We're going to show you a couple of different models, two examples, each one comparing two different models, a reduced model to a full model. The first model will only have, the reduced model will have no variables in it, just the dependent variable, and its full model will have a single independent variable. And then the second two models that we'll compare, the reduced model will have one independent variable and the full model will have three independent variables. There's a lot to look at here, so let's go ahead and get started. I'm going to use the auto data set that comes with Stata, and you can see here in line 1 I'm just going to load the data set, and then in line 3 we're going to describe the variables that we're using for these examples. My dependent variable is going to be miles per gallon, and we're going to use the weight of the vehicle in pounds, the turning circle in feet, and the displacement of the engine in cubic inches as my independent variables. I'm going to go ahead and summarize the dependent variable for you first and show you that we have 74 observations and a mean of about 21 miles per gallon. Our range of values are from a minimum of 12 to a maximum of 41. And I just want to, for a minute, show you that you can actually use regression with no independent variables. So in line 7, we're going to run the regression command with only the dependent variable. The Anova table may look a little strange to you, and of course there's no r squared, but I want you to look at the coefficient down in the regression table. And you can see that the coefficient is 21.2973. That's the value of the intercept, or beta hat sub 0. And when you don't have any independent variables in your model, that's the same value as the arithmetic average, or the mean, of the dependent variable. And you can see that that number matches up exactly with the miles per gallon average in the summarized table above. The other thing to notice here is that the total sum of squares in the Anova table is 2443.45946, and that's exactly the same as the residual sum of squares in the Anova table. And we have no model sum of squares since we don't have an independent variable in the model. This total sum of squares, also equal to the residual sum of squares, or the error sum of squares, is the first step in understanding the general linear F-test. What we're going to do next is run this model again with no independent variable, and then duplicate the model with one independent variable. If you look down at lines 14 through 16, I'm going to clear the screen. I'm going to run the model 1, which only has the dependent variable in it. I'm going to run model 2, which adds the variable weight as the independent variable. Also note that I've added an option for no table. That's going to suppress the regression coefficients, which for this video we're really not too interested in the regression coefficients. We're only looking at the values in the Anova table. Now, in this table, we can see that the total sum of squares in model 2 is exactly the same as the residual or total sum of squares in model 1, which should make sense because we know that that represents the total amount of error in a model that doesn't contain an independent variable. Now our Anova table looks a little bit different in model 2 because we also have a model sum of squares and a residual sum of squares. And we know that these are additive quantities, that the model sum of squares plus the residual or error sum of squares equals the total sum of squares. And now we can start talking about what the extra sum of squares are. The extra sum of squares are going to be the sum of squares error of the reduced model minus the sum of squared errors of the full model. And in this particular case, if we calculate those two values, we're going to take the error sum of squares for the total model, roughly 2443, and we're going to subtract from that the error sum of squares for the reduced model, that's 851.5, and we end up with the model sum of squares, approximately 1591.99. That model sum of squares in this case is equal to the extra sum of squares. Now, once we have calculated the extra sum of squares, we have to start thinking about how to put this into a test of significance. If the extra sum of squares is not very large, then the addition of that independent variable is probably not statistically significant. And the larger that extra sum of squares becomes, the more likely we are to reject the null hypothesis that there is no difference between model 1 and model 2. In other words, if we reject the null, we're concluding that the addition of this variable, x1, the addition of the variable weight of the car, is statistically significant. So we're going to calculate an f-test. Basically, in the numerator of the f-test, we're going to have the sum of squares error for the reduced model minus the sum of squares errors for the full model, and that difference ends up being the model sum of squares. We're then going to divide that model sum of squares by the appropriate degrees of freedom, and in this case, the difference of the degrees of freedom between model 1 and model 2. And then we're going to take that numerator and we're going to put in the denominator the ratio of the sum of squares error for the full model to its degrees of freedom. When we go ahead and make that calculation, we get an F-statistic of approximately 136. Now, when I did this hand calculation, you can see that it's a little bit different than the 134.62 in Stata. And the difference is rounding error, that I'm using kind of rougher numbers while Stata is doing all of its calculations with as much precision as possible and rounding only at the end. Let's move on to our next example. In line 21, you can see that I've taken the formula for the f-test and I've copied the numbers off the table to calculate the f-test by hand. And if I execute line 21, you can see I get the f-test out of the that we get from the Anova table much more precisely than when I calculated this by hand. Let's move on to the next example down in lines 28 through 30. I'm going to go ahead and clear the screen in line 28, and then we're going to run model 3, and model 3 is going to be our bivariate model with miles per gallon regressed on weight, and model 4 we're going to regress miles per gallon on weight with the addition of two more variables, the turn and displacement variables. Now you can see here that I have in my reduced model, model number 3, we have an error sums of squares of about 851, and in my full model we have a residual or error sum of squares of about 841. Remember, the difference of those two sums of squares is our extra sum of squares. And so what we're going to do in this case is construct a new f-test. In this test, we're going to have in the numerator the difference of the two error sums of squares. We're going to have the error sums of squares of the reduced model minus the error sums of squares for the full model, and we're going to divide by the appropriate degrees of freedom. Now, the degrees of freedom are equal to the number of cases minus the number of variables in the model plus 1 for the intercept. And that's why we're going to have for our degrees of freedom for model number 3, the reduced model here, is going to be 74 minus 2 because we have one variable in the model plus the intercept. And the degrees of freedom for model number 4 is going to be 74, the number of cases, minus 4 because we have three variables in the model plus one more for the intercept. And then the difference between these two numbers is 2. In the denominator, we're simply going to have the ratio of the error sums of squares for the full model divided by the appropriate degrees of freedom. When we calculate that, we end up getting an F-statistic of about 0.44, which is not statistically significant. Now, in line 35, I've gone ahead and calculated like I did above. I turned Stata into a very large calculator and plugged those numbers into the formula just to test my answer, and you can see that we get this F statistic of 0.44, which is not statistically significant. Now, these examples are to show you the relationship between the Anova table and test of significance, and to show you the flexibility of our regression models where we can test the addition, we can compare models that have different numbers of variables in them. And if we had to do this by hand, I'm sure we'd make lots of errors, but Stata has a command that will allow us to do this automatically or with less work. Down here on line 39, I'm using the testparm command. And the testparm command looks at the last model that we used, which is the one where we regressed miles per gallon on weight, turn, and displacement. And what I do here is I issue the testparm command with the name of the two variables that were added to make a full model compared to the reduced model. And when I run this command, you'll see that I get an F-statistic of 0.44, which is exactly what I got when I calculated this by hand. Hopefully this helps you understand where the numbers come for the generalized linear F-test, and more importantly, gives you some ideas of how you might apply this when you're working on your own models. I'll see everybody in class.